guess it's 11:15, so we can just start. So yes, today we will continue talking about deep learning and its application in material science. So we'll start with a brief recap of what we have done last time, and we are at the regularization part, and then we will discuss Lstm, so long short-term memory in particular, and more broadly when you have to model a sequence, and then we will go in some new directions, and towards the end of the lecture, talking about a little bit about interpretability and generative adversarial model. So that's a bit of a plan. So as last time, feel free to, it would be great if you write the question in your chat or just ask them while we go. And then we will see if we reply directly to the question or if we keep it for after the end of the lecture. So yes, I really encourage you to ask questions while I go, because it's a live session. So that is nice to get this question. Now I'll try to share my screen, and we can start. I assume you see my screen. So now we start from what we have done last time. So we said that we need regularization in deep learning. So what is regularization? So it's any modification that we make to a learning algorithm that is intended to reduce its generalization error, but not its training error, because we care about the generalization error. And we also said there are multiple strategies. You saw constraint and penalties already in this class, so we will not talk about that. And they are not so often used in deep learning. They are used sometimes, but not always. And they tend to be less used as we go in time. And but then we have the multiple hypotheses that explain that some data are combined. So these ensemble methods are quite, they're used a lot, especially, mostly, nearly exclusively in the dropout form. We'll talk about that. And then you can stop the optimization early. That's also one strategy to regularize the model. And you can also encode a specific kind of prior knowledge. And then we'll see an example, a walkthrough in this class. So we'll focus on these three, and because they're specific on the neural networks. So the dropout is a very general idea. So the idea is to inject noise into the training to promote some simpler models. So that's the very, very general idea. And that's a motivated dropout. And one notion of simplicity, if you think about it, is a function that should be smooth. And it's one of the possible notions. And there's quite some, so this Bishop is a very famous person in machine learning, and he actually proved that if you train with input noise, that is the same thing as regularizing, as Tikhonov regularization. So he actually proved that if there's a connection between the requirement that the function is smooth and this function be resilient to perturbation. So that is the general motivation for then inspire the people, in particular Srivastava and Hinton is also on this paper, to introduce dropout. And how they inject noise? They inject noise in each layer of the network, simply dropping out some neurons with some probability. So you can formulate it, this is just a very simple formulation. So you have a P, is a probability of dropout. And let's say if you have a 0.2, P equal to 0.2, you randomly drop 20% of the neurons when you train the network. And the idea is that you avoid over specialization of the hidden nuance. And it turns out to work very, very well in practice. And so this is just an example that I present to you. So this is the network. Let's say you have let me just put the pointer. So that you have one hidden layer and input and output like last time. So dropout, you will simply drop here one neuron, and let's say, and then you do a training. You do, of course, a training multiple times. So at training step one, you just drop that neuron, and then and here you see P equal to 0.2. So therefore, you just drop one neuron because it's 1 out of 5, so 20%. And then the next step, the next training iteration, you drop another neuron. And so that is the general idea of dropout. Typical values are between 0.1 and 0.5, depending really on the network and the data set. And one thing that is important to notice is that in physics and material science, you might need a smaller dropout because you have a small data set. And also, you don't have, you tend to have less noise to some extent than other applications. So if you use maybe too high dropout, then you really confuse the network because you drop randomly units. So something to consider, that if you read a paper and they use a 0.5 dropout, that's probably not what you want to do if you have a small data set. So dropout was incredibly well in practice, and that you should, that's the first thing you should do for regularization. And what happens if you think about it is dropout trains an ensemble of all subnetworks that are that can be formed by removing this the units in the internal layers. So you think about this: you have a base network, and then you do lots of training iterations. At the training iteration, you say, okay, that's your network that you're going to train on because you have dropped this, and then the next iteration you're trained on this network. The next iteration train on this network. So it's a way of seeing that is an ensemble of some networks that's quite a complicated one, because all these networks share some level the parameters, because some units are still there. So that is one way of thinking about it. Some additional consideration is that it's very computationally cheap, because you just drop stuff and it's very, very fast. And it works with nearly any model, and this is that's why it's so used. When you have very, very few samples, it might be less effective, as I was mentioning before. So if you have very, very few samples, but you can always fix the let's say this dropout ratio. Let me finish, and then I look at the question. So, and also it turns out that if you keep dropout at test time, that can be considered as a heuristic to predict, so a heuristic for estimating the prediction uncertainty, because essentially what you're doing if you do it at test time, dropping networks, not dropping hidden units, that means you do it, I don't know, 100 times. You predict 100 times this your quantity of interest, dropping randomly some hidden units. That means you have 100 different networks, which are kind of, they share, of course, the parameter. And if they all agree, that means you are kind of certain about the prediction. If they start to disagree, then you can use that as uncertainty. And this is a very nice work by Gal and Gamarani at Cambridge. So then let's see about the question. So yes, so there's a question by Luca regarding the Bishop and Tikhonov regularization. So essentially, what's the difference? I will maybe. So that is, we can come back to that maybe at 12:45, because now let me see how short it is. So now I can read it. Okay. So hi Angelo, you say that Bishop proves that Tikhonov regularization is equivalent to introducing noise in the input, but then you discuss dropout. Noise induced in the inner setup of the network, which is not the intuitive understanding of input. What about the literal noise added to the input? Noise added to the input descriptor of the data points. Yes, so that was the motivation. So actually, that inspired the people of Dropout. But of course, the noise is added to the internal layers and not the input. Regarding the corruption of the input, so in Dropout you don't use that. So yeah, you really just do it for the internal networks, because it's typically because people think that if you drop the input, you haven't learned what to drop. So that's the intuitive explanation. Yeah. So that is my answer to that. And then Max is asking about dropout. So what would it make the optimization more slow, since the model is changing at iteration? That's correct. So you're right, Max. So it's very computationally cheap, because you dropped some units, but it will take a bit longer to train the network. So you have to pay that, but you cannot know it in advance. But it's generally not too much in the sense of it's not 10 times more, you know, and it really depends on the application. So, but that is something to consider for sure. Yep, cool, great that there are questions. So then we can continue regarding another technique is early stopping. So when you have, it turns out that when you train large model, that you have enough capacity to really learn, let's say, not learn, but really copy the input and then, let's say, not really, so to overfit completely your task. And then you can see that if you look at the loss function and you plot the loss function against the model complexity, so you will see that if you get a bigger model, and the training loss will continue to go down across, let's say, I mean, you can put here also iteration, but then the generalization loss will go up. So there's kind of optimum that, because you remember, we care about the generalization loss, and therefore you can stop earlier, and one can say, okay, when the generalization goes up, then I stop the training. So that is early stopping. Is used, yeah, pretty much in all the training in neural networks. And what you do, you train, and then when the validation error goes up, then you stop training. So this is the effect. The intuitive explanation is that you have the effect to restricting the optimization procedure to somewhere around the initial parameter values. So, and actually you can show that if you have a simple linear model with quadratic error function and gradient descent, then early stopping is really equivalent to L2 regularization. So that's a proof. It's quite easy for in this book. So it's really this intuitive understanding that if you just take not too many steps, you stay around the input values and of the parameters. And then you can also use it in conjunction. So early stopping between other regularization technique. But of course, you require a validation step. And so that is a downside of this procedure. So you cannot use all the model for training. Maybe anticipating some questions. So one could also do cross validation and all these sorts of techniques, but usually it's not done in deep learning, at least in the general setting, because it's very computationally expensive to train a network, and therefore you will not see it done in general deep learning literature. But there's nothing to stop you doing it, especially it might be a very good idea in the material science application setting. So then, yes, one slide regarding the physics and material science regularization. I would say that data is usually scarce. So be careful in overfitting, because overfitting is very high if you have a very few data points. So really be careful in testing the generalization ability of your model. This is more thinking about if you develop your own deep learning algorithms. And then one important question to ask yourself is like, how different are the training, validation, and test set? And sometimes it's not so, you need to think a little bit about that in material science and physics. Imagine you have a molecular dynamics simulation, and you take 50% of the training configuration and training set and 50% of validation set. You say, okay, I have 50% validation set, so that's a big validation set. But if you think about it, that's probably a terrible idea, because the validation set is maybe nearly exactly the training set. So you're really not testing the generalization ability of your model, but simply overfitting and not realizing it. So there are also more subtle situations, but always ask yourself how different they are. And so maybe you can also think about that, if there is some, let's say, transformation that you apply. Let's say you have some input structure, and then you represent that by a descriptor, and this representation put maybe together the training and the validation set, for example, and they arrive at the same vector. That's also something that is more subtle, because if you look just at the structure, they are different, maybe for training and validation, but when they are represented, maybe for some reason they are different. So look at what's the input of the network, and that will tell you how actually different this validation training, validation, and test set. And also one thing that could be also helpful is that test the model, maybe you could think about testing a model on a data that is different from the training for physical reasons. So the idea is a thing that what we have done is that, or other people have done too, that you have a pristine structure, let's say perfect structure that you use for training, and then defective structure for testing. So it's really, these are different for physical reasons. So that could be something to think about, or maybe you can change the chemical composition an alloy, for example. So that could be something to think about. So this is about regularization. So then we have some, we have a question, that's great. So yes, generally the training data is divided randomly into batches to pass through the neural network model. So do the order of the data, if it is not random. Let me read it again. So the training data is divided randomly into batches to pass through the neural network model. So in principle, the order of the data could make any difference in the training. In principle, yes. In practice, you do, I mean, just make sure that you shuffle the data before, and then usually in practice it's not so, it's not a problem. To have the order of it. But in principle, yes, because you don't even go to a global minimum when you have gradient descent, for example. So yes, you're expecting different local optimum to some source. There's actually something called curriculum learning that is really that people like try to figure out which examples to get to the network first. So that could be used in some setting, but in general, my suggestion would be to shuffle the model, and then it should be, it should be no problem. What you should try is maybe change the random seeds when you start, and really see if the prediction are really staying the way they are. You train network number 1 and you train network number 2. And then just changing the random seeds or the optimization procedure, and then you can always see if the performance is similar and get an ensemble of networks and predict that. That could also, that is a good way to proceed and take care of that. Yes, so then we can continue. So, I now go to some example of material science in fully connecting neural networks. So there was a tutorial by Andreas, and then he showed for a regression example. And here I will just talk about briefly how people use a very recent work when people use fully connecting neural networks, so what we saw now, to solve the Schrödinger equation. So these are the two works that are very recent, and I will give you just a feeling for how they work. And that's an application on real life material science of deep learning. So you all know the Schrödinger equation, so we're not going to the details. So you have you need to find the wave function that is an eigenfunction of the Hamiltonian. And the Hamiltonian is written here for the electron system, so in an adiabatic approximation. You know very well what I'm talking about. And if you remember for your other classes, that you can solve for the lowest energy solution in naught via the variational principle. So you will find some wave function, some trial wave function, and then you calculate the energy of this wave function, and then you try to minimize this energy, and for the true solution you will have the minimum energy. So the true ground state psi will have the minimum energy of the system. So that is a variational principle, and you can do this integral. And so I'm no expert in that, but it's the way it's solved currently. The gold standard is variational quantum Monte Carlo. So you have this answer, and just for the purpose of this discussion, it's just good to know that one wants to directly minimize the energy of the system, and you do having a parametric approximation of the true wave function. So you have an answer, you start calculating this integral, and you get an energy, and then you improve these answers, getting better and better wave function as you go, and then minimizing the energy. It's called Monte Carlo because you're sampling these high dimensional integrals. It's very complex to calculate. And what you do, you optimize the parameter in the trial wave function to reduce this cold variational energy. And yes, there are some answers that are motivated by physics, and this is how what the quantum Monte Carlo community has been doing. with very good success, and there is some motivation for why you choose a given trial wave function. So this is in one slide, variational quantum Monte Carlo. That's not important to understand the detail, but we will see how then these two papers that I showed you use fully connecting neural network to solve this problem, to solve this problem. So the idea is that you want to solve the Schrödinger equation with deep neural network, and essentially what these two papers have done, and was actually started by Carl in 2017, you use the artificial neural network as a wave function ansatz and you use that to and you put it in the variational quantum Monte Carlo framework. So essentially, instead of having on top, or instead, it depends on the application of having a trial wave function that is motivated by, you write your trial wave function, optimize the parameter. They try to learn this trial wave function through neural networks. So, in particular, Polynet, that is by Hermann, that was actually at the Fritz Haber before. So they proposed this wave function ansatz that is quite similar to the variational quantum Monte Carlo you saw before. But the difference is that this something called gesture factor J and backflow F. That is, you can see it, it's not very important, the details, but these are represented by deep neural networks. So they learn the wave function ansatz using multi-layer perception. And they also use, they encode the physics. So they start with some physics, incorporating artery fog and some electric cups. That's not so important. So they start with some physical ansatz, let's say with artery fog, and then they learn to a fully to a fully connected network this parameter. And a similar idea is done by Fao and all from DeepMind. So they use here, they don't use any physically motivated ansatz or guess. They really just they say, okay, we want to have a wave function that is antisymmetric, and that's the only thing they built in their network, and they have components of one electron integral and two electron integrals. They come up in different places of the network, and then they just use they enforce the antisymmetry of the wave function, and then they get the psi out. So there are two different ways to approach the problem. All of those use fully connecting neural networks. And so essentially what they do, they solve this equation that from the variational principle, and minimizing the total energy, and they solve using as a functional approximation a deep learning network. And if you remember the discussion we had last time, this is actually it's not in the true sense a machine learning problem, but it's really a pure optimization problem, because that from equation from physics that this is the right equation to solve. So that is so here you can think that these deep neural networks are used because they are very, very flexible function, and you already know so it's a optimization problem solved by deep neural networks. And that's actually coming back. There was a question by Luca last time. So he asked, why don't you use sometimes we don't use a second order method? They actually do in this paper, in the Fao paper. So that is. And it turns out to work quite well in practice, mostly because the deep learning is a very flexible approximation. So as you remember, you can express a lot of functions with that with neural networks. So that is probably where the idea comes from, to solve this optimization problem with neural networks. And it's early days. They did some atoms and small molecules. There's no solids yet, but they are able to get recover between 97 and 99.9% of the electron correlation energy for some systems. Yes, so this is for reference 1 and the reference 2. This is what you can see here. So it looks like they are on the right track using neural networks. When you have bigger system, the computation takes an awful long time, can take days on the GPU. So that is maybe a downside that will be solved with time. But it's also here is an interesting application of how can use fully connecting neural network to solve a material science problem. So then I would say maybe if there are additional questions, I'll take those. Otherwise, we can continue. We switch a bit gear, and we go to a special architecture, which are convolutional neural network, and then we will show how you can go from fully connected neural network to a convolutional neural network. Right. Always feel free to type in the chat as we go, and then we can take questions like this. So let's think about it. So now we have a multi-layer perception, and we don't assume anything about the input of our data. And that is often, I mean, sometimes is the best you can do, and it's a very good thing to do, not to assume anything. And this could be, think about, people refer to that as tabular data. So you have example as row, and then you have features as column, and you don't assume a priori how the features will interact. And sometimes it's appropriate because let's say you want to predict a property for atomic features, then you have material 1, material n. This is just, I made up these numbers. You can have feature 1, feature 2, feature 3. You don't know a priori how they'll interact. And so then it makes sense to use a fully connected neural network, because everything interacts with everything. Right? Every neuron interacts with every neuron, and of course every input feature interacts with all the input features. Another example would be if you have a basis set expansion, it might be appropriate to use a fully connected neural network as well. But let's say you have, but this comes at very huge cost because you connect everything with everything. And let's say you have a STM image that is 1 megapixel, then you have 10 to the 6 pixel. And then if you have one hidden layer with 1,000 units, you already have 1 billion parameters for just one layer. So it's a huge computational cost. And so that's why people started to think, oh, but what if there's some regularity in the data? We can come up with architecture that can actually exploit that. And this is what we're going to see that as an example. So convolutional neural network, a specialized kind of neural network architecture. And they're used to process data that is kind of grid-like topology. That's one way of defining that. And you can think about the 2D grid of pixels. That's a grid-like topology. So images could be X-ray crystallography, STM images, whatever you want. And then you have a 3D grid of pixels. So you have volumetric data, and this could be magnetic or electric field, for example. And you can also have 1D grid of samples, and then you could be a time series data, a spectra. So these are still problems that can be tackled by CNN. So now we want to, let's say there are two, we want to build in some knowledge in the network of what we know about the data, and there are two guiding principles for the CNN. The first is called equivariant representation. So the network should respond similarly to the same, let's say, to the. So if you have an equivariant representation, so if you have a shift in the input, then the output should shift in the same way. So we get an example in a moment. So that's equivariant representation. So it doesn't, the output of the network doesn't really depend on when you apply a transformation, in which part of the image, let's say, you apply the transformation. And then the locality principle is that if you have a grid-like topology, then there's some degree of locality. So that means that nearby pixel, so there is some notional locality. So if you see in an image, for example, nearby pixel, they tend to have a stronger connection. Let's say that's the locality principle. And for example, if you have the principle of equivariant representation for images is that if you move an object by 20 pixels in the image, the output signal will just be shifted by 20 pixels. So it's really, this means equivariant representation. And locality principle is that imagine that only a small neighborhood of pixel is used to compute the corresponding in the representation of that given pixel. And you do, I mean, this is locality is very well known in physics, so you know, you already encountered that in lots of physics modeling in solid state, for example. And And this is quite clever because you can exploit the grid-like structure of the input data, and therefore you can reduce drastically the number of parameters. So if you think about it, it's a very smart way of regularizing using the structure of your data. And this is a general principle. So people would come up with specialized architecture trying to exploit in the neural network, let's say, so in trying to exploit the input data structures. And so now I want to really briefly give you an understanding of how the network is work and why they are convolutional. They're called convolutional neural networks. So we just get a refresher of what a convolution is. I'm sure you saw that in your classes in physics, but just write it down like this. So if you convolute f and g to function, you take a function f, and then you take a function g, you shift, and then you slide this function g across function f, and that's the output. That's the convolution. But this is the mathematical formulation. So the intuition is essentially measure the overlap between the function f and g when one function you flip and you shift by a given amount. And so cross correlation is something similar, and it's just changing a sign of that. So just keep that in mind because it will come back soon. So now we have a convolution, and then you can have a discrete version of that. So you have, let's say, the integral, and then this is the discrete version. So you have f of a times g of I minus a, and you sum over a. So that's the discrete convolution in 1D, and you can do it in 2D. You just simply add an extra parameter. So this is because we will show an example with images. And the discrete cross correlation in 2D is simply the same as this this equation, but you just flip the sign. So gi plus a and j plus b. So this is how it looks like. So that's a discrete convolution. Now, how do we go from an MLP, what we saw before, to the ConvNet? And we said that we want to build in this knowledge of having, the equivariant representation and the locality principle. So the example, we take 2D images and this X as an input, and then we define the first hidden representation as H. So we just look at the first hidden representation for the purpose of this discussion. So let's say X, ij, denote the pixel ij in the image, but you can imagine that's like, STM image or whatever image that is motivated by physics. And then we have hij, that's the pixel ij, the representation of pixel ij. So in the MLP, remember we had weights, and then we have wij weights. In this case, we have a fourth order tensor because we have a 2D input, and we will get a 2D output because you have a 2D input, which is the input image, and you have a 2D output that is a hidden representation of that pixel. So you will have a fourth order tensor, and you are the biases. So this is we can express the fully connected neural network layer in this very simple formula. When you have a output hidden representation of pixel ij, you have biases, plus you have this fourth order tensor times the value of that pixel at the value of the input image at KL. And you see you have you can interpret this as a weighted sum of the input pixel, right, weighted by W IJKL. Now we do just a small change of indices. It's not it will come back. It's important just for later. It's just changing the indices between. You just rename K as I plus A, and then L as J plus B, and then you just substitute, and that's what you get. See IJ, and then I plus A and J plus B. Now we need to sum over A and B, and this is also the change here. Now let's say, okay, now we define W, IJ, and I plus A, J plus B as V of IJ, AB. That just, I can always do that, right? It just depends on IJ, AB, so I can just rename that. And we substitute this here now. And so that's how it looks like, right? So you have now V. And now you see that for any given location ij in the hidden representation, we compute its value simply by getting the summing the over pixel in X, center and ij, and we weight by this 4-folder tensor. Now let's apply the principles that I told you about the CNN. So the first principle is equivariance representation, and the second principle is locality. So we'll start with equivariance representation. And how we can build this in. This is still a MLP. We didn't change anything, just did some index change. And so what we want to do in equivariant representation, so shifting the input X should simply lead to a shift in H. How do you do that? Well, the only way to do that is, so that's the formula that we had. So this is only possible if V and U do not depend on the pixel or on I and J, right? That's the only way that you have the same shift. So therefore, we say, okay, now we define V, I, J, A, and B. It just depends on A, B. Doesn't depend on when I am in the image. And then we just rewrite that in the. So then this is, you can just call U, I, J is a constant. So then you rewrite this equation as U plus sum over A and B of V, A, B, X, I plus A, J plus B. See, instead of having a 4-folder tensor, you have a second order, you have a metric. So you say that's how you save the parameter. So you have a huge saving parameter, just adding that you want to have the equivariant representations. And now we are here. So now let's so that's our representation. So let's look at the cross correlation. Remember, we just looked at this before, and it was you have F cross correlated G with ij, it was the sum of A and B of F, A, B, G of I plus A, J plus B. But this is exactly what we just did, right? This is F of A and B, that is V, A, and B, and this is X. So it actually is adding this equivariant representation, turns out that you have a cross correlation, not a convolution, but a cross correlation. And that's why these networks are called, actually, there's a misnaming, so they are called convolutional neural networks, but they should be called really cross-correlation neural networks, but it doesn't really matter. So then a VAB, as I said, is many fewer parameters because it doesn't really depend on I and J. And so that is, yeah, that's a huge saving, a smart regularization. And then we just finish putting the locality principle in. So now we don't have any locality principle yet because we sum over all A and B. We can go as far as we want from the pixel I and J. Then if we just look at around I and J, then we just limit this sum. And this will implement the locality principle. So we say if A is bigger than some delta, I don't know, 3, I just look at neighboring pixel, 3 neighboring pixel, when I compute the hidden representation of a given pixel. So that means that you have, we can just do that, you limit this sum, and then you say, okay, now I sum only between minus delta and L in delta. So I really look at the vicinity of the given pixel. And this is what it is called the convolutional layer in the neural network. So you see that applying some idea about the data, we are able to come with a specialized architecture on, and these are the convolutional neural networks. These are called convolutional kernels or filters. Is VAB. And yeah, so maybe I'll stop for questions if there are any. All right, so then we can continue. So then like in practice, so the intuition behind that is this was the mathematical formulation, and when you actually compute a convolution, as you see, you just slide the filter across the image. So this is the filter K example. Let's say this is a small filter. These are the V's that we saw before, and you slide across the image. That's how you compute your output representation. And then you see that you have this sliding. So you have let's say this kernel. It's a small kernel, and you slide across the image. Here I give you an example. So you have the image, and then this is the kernel that you have. You multiply the two, so the kernel times the matrix, and then you get an output that you sum all the elements and you get the output here. So you will do 3 times 0 plus 3 times 1 plus 2 times 2 plus 0 times 2, and that's the output is calculated. So that implements the locality principle and also the equivalent representation. That's the convolution. And it turns out that you do a lot of convolution actually in Photoshop when you do image, to treat the image. And here you see that if you have just a small kernel, we really change the image. So here you have Max Planck, and then you have if you have an identity kernel, that's just, and you slide across the image, that you just remain the same image. But then if you just slide this small kernel across the image, you will blur the image. Or if you just this small kernel across the image, you will just extract the vertical lines. This kernel will extract the horizontal line, these edges, and this will give you a 3D effect. So you see that with a very small matrix, then you can extract lots of features from the image. And the key is that, so why the two principles are satisfied? Because you have equivalent representation, so the same kernel is applied throughout the image. And then the locality principle is because the kernel size is quite small. It's 3 by 3, for example. And the idea is that in neural networks, instead of having this kernel fixed, you learn the kernel, minimizing your target. Let's say you minimize your classification error, and then you learn these filters as you go. And so that is the idea. So these kernels that I show, they always have the same features. And in machine learning, you just extract out, you learn automatically these kernels. And this will depend on the task that you want to accomplish. And so I would say then you can aggregate representation. That's not very important. We can skip that. So, but you can build, and you have a series of convolutional layer, and this will give you some intuition, high-level intuition of the image, and build a global representation, stacking different convolutional layers. And we can skip. And then I'm looking at the time. So let me finish this part of the CNN, and then before the material science application, we can have the break. So then this was actually done. Sorry, there's a misspell. So it's 1998. So the first convolutional neural network was spun by LeCun and was made to classify handwritten digits, the so-called MIST dataset. And the neural network is it's a bunch of convolution. Then pooling is not very important for our discussion. And then like you have another convolutional layer, and then you have a dense layer at the end when you flatten all your convolution. And so using convolutional neural network, it was able to classify this postcode. So it was arguably the first breakthrough in machine learning when people really were able to classify real images with CNN. And now people do much more complicated stuff. And so, for example, this is YOLO, just a motivating example. This is still a bit old, 2016. But with CNN, you can even detect object in an image. Let's say this is a person detected in a piece of art, and so you can really people went much further from just a written digit to real life images. So there's, for example, object detection on CNN, and most of the work is done on images on CNN. You can also colorize images, which I find quite interesting with CNN. And yes, so maybe then we stop for a couple of 4 or 5 minutes. So then we can take some questions. My time is it says 11:59, so we come back in 5 minutes. And in the meantime, I can take questions for if you have any. Yes. So what about convolution in 3D or higher dimension? Yes, there's nothing that stops you to have convolution in higher dimension. So yeah, so if you have volumetric data, for example, then it might be a very, very good idea to apply this convolution. in higher dimension. You just have filters that are in higher dimension. Yeah, people have done that. So in for volumetric data, and yeah, so that is about that. I don't know if this answers your question, or should I elaborate more, Luca? Yes. So Max says the idea of discrete kernel for image sounds a bit intuitive to me, but I've seen some CNN models for materials, for example, SHNet, that actually use a continuous filter convolution. How it looks like in practice. So yes, so I'm not an expert on this SHNet. We have I know that SHNet is a type of network that is can be framed as message passing network. I have a couple of slides about that, but the detail of the convolution of how the convolutional filter is applied, I'm not sure. The matrix is replaced by a function or something like that. Yeah, I mean, I guess you need to, when you have if it's no longer discrete. Now, when you have a multiplication of the kernel times the grid-like data, right? And you know to multiply which with which, right? Because you know the positions. Now, if you want to have a convolution on I guess a continuous way of multiplying, we'll have to deal with we'll have to solve that part. So I don't know if a matrix is replaced by a function, or if it is this product, right, in the convolution, if it's this product replaced by a function, and you still have two matrices. That I don't know. You need to look up the paper. So we will continue with a couple of examples of CNN applied to material science. So this is from our own work when we use the CNN to classify crystal structures. So our goal was given prototypes. So these prototypes for elemental solids, we wanted to say, okay, now I get an input structure. What is the most similar prototype to it? And we wanted to be robust with respect to atom removal and deformation. So these are some examples. So we were able to, we represented the input structure as an image. So it's not really important for the property discussion, the details, but imagine that you have a structure and then you build in some symmetry, looking at some sort of diffraction, and you get an image out. And it's an RGB image. So so then we apply the CNN, and so then you see you have convolutional layers, and we have some pooling operation. Downsampling is not so important, but we had yes, like a 6 layers, so deep learning, and then putting together convolutions to arrive at the classification. And you see that the kernel is quite small, 7 by 7, as I was telling before. So you just need a small kernel, you slide across the image, and then you can have very high accuracy of classification. So that's one example that you could use a CNN for. And the grid-like data here, it's an image, which is, you can see as an image, it's essentially a 2D array, right? And that's hence the grid-like topology. And what we also did, which it's useful, I think, to think about in any material science application, to try to understand the neural network, what the neural network learns. So we said that we have an input, we have 4 paths, and we have an input layer, we have a series of convolution with non-linearity, pooling is not very important, and then we get to the next layer. So we go from an image to the classification. It turns out that, and there's some very nice paper from 2014, that you can actually try to reverse this let's say flow, and looking at what are the most important part of the classification, most important part of the image to arrive at the classification decision. And so you can show, I'm not going to detail because there's a hands-on example as well by Andreas, but you can show that since you know the operation that you apply, the convolution or pooling, we can skip that, then you can go back and look at what are the most important part of the image for classification. That's what we did, and it turns out that the CNN is able to learn physically motivated representation to look at where a human will look to classify this image. And as we saw already in the first lecture, so you can see that the network clearly gets more abstract representation going deeper into the network. Because here you see more, the network is looking at more dots to classify the image. So that is to say that you can interpret CNN, and that is something that you should really think about, since your application is science. You really want to understand why you arrive at a classification decision. Another application that I find interesting is that people use the CNN for detecting atomic position from experimental STM images. So they have an experimental STM, and then they use a convolutional neural network, in particular fully connecting neural network, to get out the atomic positions. So here, so you will get this STM, and then out you get really coordinates of where the atom should be. And this is done through fully convolutional neural networks. And the way it's done is that you have they start with an input image, and then they use a U-shape fully convolutional neural network. So where they have, instead of getting an output one single classification, let's say, okay, that's prototype 1, prototype 2, they get in output a pixel-wise classification. So at each pixel, they can say, okay, this is our prediction. And so that's called fully convolutional neural network. And what I found quite interesting is also that they train using simulated theoretical images to train their network. And then they apply the trained model to experimental data. So that's what I meant before, to make sure that your training is different than the evaluation. So that is something interesting. And that's also point out to something that is good for material science, that you can sometimes generate your own training data from first principle, and that's a big advantage. So you can solve the DFT with DFT calculation, Schrödinger equation, and you can generate your own training data, for example. So that is something that usually you don't have the luxury to have in machine learning, and you can exploit that. And briefly, another application. So there's crystal graph CNN. So here they use a CNN not from images, but to represent structures. And in particular, what they see they see a structure as a graph where nodes are atoms in the crystal, and then edges are the bonds between neighboring atoms. So that's how they represent this, and these nodes are represented as the vectors, that they have atomic features, and then edges that are, they have distance information between the neighboring atoms. So they have these two inputs, and what they do, they actually have features vectors that are initialized, and then they use a convolutional function. This is the choice of convolutional function, not going to the details, but to update these feature vectors, and they do that through convolutions. And so that means that the convolution is because the filter parameter are shared over the whole graph. So so that's why it's a convolution, and then you see the mathematical formula for that. So then you see that you iteratively update the initial features that are starting with atomic features, and then you kind of learn that from your prediction to change these initial features and tailor them to your model. And they have achieved this. They apply that for the prediction of formation energy of inorganic compounds. So they achieved the root mean square error of 78 milliev. And there was a couple of different people working on that. And what you mentioned, Max, before, that's SHNet. And these crystal graph techniques have a similar accuracy than SHNet, although they, as far as I know, they didn't test on the exact same data set. So, and this is actually, turns out that is a general way to do things, this update, that you pass through the network, and then you keep updating your representation. And this is something called message passing neural network. And so the idea is you represent the molecule as a unidirected graph, and atoms are nodes and bonds are edges. And what you do, you have message passing phase, where you transmit information across the network and you build a neural net representation of these nodes and edges. And that's one realization of that was the crystal graph. And you see, this is simply a notation to say, okay, now you have edges. So you have nodes, the states of the networks, and then you have the edges, and then you update that recursively. And then after that, once you build this representation, you have a readout phase when you say, okay, now I have a global representation that is built up of this single unit, single part, and then I make a prediction. So these are people call them message passing neural networks. And the prediction of the readout phase could be information energy, as I showed before, or HOMO, LUMO, or maybe dipole moment. That's mostly for molecules, for example. So that is for all for CNN. And so then I'll move to the next part if there are no other questions. So now we'll switch a bit gear, and we'll go into sequential data. And then I also want to introduce some miscellaneous work that I think it's quite cool and you should know about that has been recently done. You should be able to see that. So now we switch gear, and we go to recurrent neural networks. So now the reference of the class is the same, so we can just skip. So now we saw so far tabular data and grid-like data. So, but what happened, and there's always a key assumption that the order doesn't matter. So images, I take a STM image of graphene first, and then boron nitride second, and I train the network. Doesn't really matter, right? So, but what happens when the time matters? When data are not independent and identically distributed? Then you have a sequence in that case. And there are lots of applications about that. In deep learning, you have speech recognition, music generation, sentiment classification of text, because text is a sequence. Obviously, in material science, you can think about experimental spectra. In general, any temporal signal that is a sequence. So the order matters on which data points you take. Or maybe, and I know there's some work on that, when you have you can think about a molecule as a sequence, and then this you can see, okay, now I need to take care of, it's no longer data points that are independent, they really are a sequence. And you see that in everyday life, right? If you want to predict the stock price, let's say you have let's say xt is the index value at time step t, and then you want to predict what is, you have all the history from 1 to t minus 1, and you want to predict what's going to be the stock price as time t. Then you have a sequence. And then you can see, I don't know, I put it down the SP500. So there was a coronavirus crash, and then you see that then after there's some sort of recovery in the market. So to get this behavior, it's important to know the past. So the prediction of the future, it really depends on the past. And that's when you have a sequence. And how do you do that? Well, it's complicated, right? Because the input of time t will depend on all previous time steps. And the more time step you get, the more complex the prediction task at hand. So you need to make this tractable, because you need to say, okay, if I have a long sequence, how do I remember things that are important from the sequence? And so the goal of sequence modeling is really to find good approximations for that, like we did in the CNN before. So there's something called autoregressive models. So let's say you have an entire sequence from 1 to t minus 1, and they say autoregressive models say we don't care about the whole sequence, we just keep a short time span before time t. So you say tau, for example, I take tau equal to 1, and just look at the previous time step, and this is first order. You can think about the first order Markov process, just think about the previous time step, but you can in general keep different tau, right? You look at 4 previous observations, and then you can apply the MLP. But this is a bit unsatisfactory, because how do I choose the right t, right? And this is even a right t, and this tau, not t. So how many steps in the past I look to predict the future? And And so what the neural network and the recurrent neural network trying to achieve is they learn to keep only relevant information about the past. And these are called latent autoregressive models. So the idea is that you introduce a latent state, it's called HT, and this HT, by definition, summarizes all the relevant information about the past. So what you do is say, okay, now I have, let's say, at every time step. So at every new time step, you look at you have HT that summarize the past. So you say, okay, I have HT minus 1 that summarize the past until time step t. I have my input at time t, and then I have a new representation, and you do that recursively. So so essentially here you see the, sorry, I should put the laser pointer. So here you have a prediction at time t. Instead of depending on all the past, explicitly, you say now the prediction at time t only depends on the hidden state at time t that summarizes, by definition, all the previous time steps. And that's the idea of latent autoregressive models. And then this is just how to think about it. So you have an input data at t times minus 2. Let's say you want to have a sequence up to now and you want to predict tomorrow. Then you get this latent state plus the input state at t minus 2, and then you predict t minus 1. And then now you have t minus 1, and then you pass over the hidden state, and then you predict at time xt. And you continue doing that in this way. So the idea is to really have a latent state that summarizes the past. So that's the goal of RNN. They really learn this mapping. So to summarize, right, to summarize the past in this latent state, this is what RNN do. So RNN is the way to, and this is, yeah, we can skip that. So what you do now, you have an input vector, xt, and now instead of, you remember before, we only have this part, the multi-layer perceptron part, but now we also have a hidden state that we pass along. So we have an extra term here that is that summarizes the past. And this is just the hidden state of a recurrent neural network. And then you output the vector looking at from this hidden state. And there are, so if you think about it, you have MLP. So it was just or CNN, you get an input, neural network, and output. Here is more a many-to-one. Let's say you have a sentiment classification, or you want to get you have a sequence, and then you predict an output of a sequence. You will have different inputs at different time steps, and then you get one classification that is a many-to-one. Let's say you have a spectrum, and you want to predict, okay, you have all the frequencies, and then you want to predict, is that an insulator or I don't know, a conductor, right? So that is the many-to-one mapping. And then you can have even many-to-many mapping. So you have an input as a sequence, and you also return as a sequence. That's also possible, and actually it's called machine translation. Yes, there's a... in RNN, when you say summarize the past, do you mean that the hidden block act as a feature extractor in a similar sense to CNN do for images? Yes, exactly. So that is really a very good way of thinking about that, Max. Exactly, because you summarize, so you extract what's the relevant information from the past. And so that's not so important. We can skip that part in the interest of time. So training, it's so you always have this mapping, and so essentially training is more complicated because you have lots of time steps, and you need to back propagate in time, and you have a repeated application of the chain rule because you have multiple steps. And it turns out that actually that's a problem. It's a very big problem, and you can show that. You remember that we calculated the DJ, the loss function, with respect to our parameters in the first lecture. It turns out that you can, that this is the mathematical formulation for that. And there is a central quantity affects the numerical stability. And it's this one, you can show that, you can look at the details here. But you see here, what's important is that you have a product of the same matrix, t minus 1 times. So you're always multiplying for the same for the same metrics. And if you have large powers of a matrix, you know that that these things can get very big or very small. And that is what is referring to as exploding and vanishing problem in RNNs. So that means that you have a W and you look at the eigenvalues, for example. Then if these eigenvalues are greater than 1, you keep multiplying by that. You have exploding gradient. That's easy to fix. So you have a gradient clipping. But then the hardest part is to vanishing gradient, when like the product gets very small, because we know that the network learns through gradients. So if you don't have any gradients, the network will not learn. And this is called vanishing gradient. And for that, and there were some architecture that were developed. And the most important one is called Lstm. So it's long short-term memory, because you want to get rid of this problem of vanishing gradient. So this we can skip. So the main idea is, as we were saying before, that you need a built-in mechanism for a RNN to remember all the relevant information, like you also, Max, were saying. And then the idea is really just to have a memory part of the network. This is Lstm. We will not have the time to go into the details of this, but what they are is simply you have a hidden state, and you have a memory cell. This memory keeps track of the information that you carry over from one state to another, and this hidden state is responsible for changing this memory. Imagine like as a computer that is carrying over this information. So you don't have to propagate the information through gradient multiplication, but you have a cell memory that is there and stays there. And in this way, you can get rid of the problems of vanishing gradient. So and how do you access the memory? Well, there are some. That's why you see this structure. So you have some gates that they say, okay, now I have a memory and I want to update what I know because I want to summarize the data that I have, right? I want to extracting the information. And then there are gates that you learn how to say open the gate and change the memory or forget what you have. So that you can learn always through networks and through fully connecting neural networks in particular. Yes, so Luca, are you aware of any diagnostic to be applied to the available data in order to decide whether an RNN is a proper model? For example, if the Markov layer requirement is met, or does just one try the RNN and see if it works? The point I want to get is how much understanding the user needs to have about the assumption behind a certain architecture in order to proficiently use it. Yes, so I'm not aware of any diagnostic to be applied to see if the RNN is the appropriate model. So that is, I guess, I don't know if there are any new work on that. For sure, there's also something new that happened. It's called attention mechanism, and for that, there's I don't know. I really don't know if there is something to know about that. What the main assumption, maybe Luca, to come back to your question, is that you have this mapping doesn't really change across time. So that's something to keep in mind. So if you're it's kind of a stationary process. So that's something that you can think about if you think that the way to summarize your past is stays the same. That is one way to look at that, but I'm not aware of any quantitative way to do so. And now we can skip all of that in the interest of time. Sorry about that. So we have lots of application of Lstm. So there are time series, prediction, speech recognition, undiction recognition, sentiment classification. And for example, Google Voice uses LSTMs, and Google Translate uses LSTM at least at 2016. There's a new kid on the block. It's called attention-based system. So if you're looking at modeling time series data, that's probably also what you want to look at here. attention-based system, but LSTM are still used today, even though they were proposed like a long time ago. And an example that I looked at is that I saw in material science that is very recent, is one that people were able to reveal ferroelectric switchings using deep recurrent neural network. So essentially you have a band excitation piezo-resistant force microscopy. Is a technique that is allow you to to look at the nanoscale switching process. I am no expert in that, but what is suffice to say is that the author say that the raw data is high dimensional, and there are like they measuring lots of let's say characteristic of the system, but it's not they know that the information of physical significance lies in a lower dimensional manifold, but they don't know how to predict that in advance. At least that's what they say in the paper. So the way they have done that is to stack recurrent neural network, in particular LSTM, one after the other. Here they use something called autoencoder. So they have raw data in, and they want to reproduce the raw data out, but they want to have a very compact representation. And so that you see is called embedding layer. So you have a raw data, and then you pass LSTM. You have different layers, and then you go kind of a bottleneck. You learn a lower dimensional representation. And that they have done to LSTM encoder, and they claim at least that the embedding layer here learned through the LSTM is really allows them to look at the manifold of physical significance. And they also argue that they were able to do that only with LSTMs and also recurrent models, and not with I don't know, multi-layer perception or other techniques that are not based on deep learning. So that is an example. And then we have 15 minutes more. So we will look into quickly in GANs and then some interpretability. So let's see. So far, we had something, we looked into descriptive model. So you have yes, I have a question. Let's see if I take it now, or maybe I take it 12:15. Yeah, maybe I take it at 12:45 when we are done with the lecture. So discriminative algorithm. So we have an input feature xi, and we want to predict yi. So we say how likely is yi given xi. That's the prediction. So the features are an input, and then the output is a classification or regression task. And an example is I have the words in an email. I want to predict if that's a spam or not spam. Material science is like I have a chemical composition and the atomic positions, and then I want to predict the superconductive temperature. Now, generative model is I find them very, very interesting. Is that you do the opposite way. You give an yi, so the prediction, so the class, and you say how likely are the input features xi. So instead of predicting a label, you attempt to predict the features that generated that label. So P of xi given yi. An example is like, assuming this email is spam, how likely are these words, right? And I think it's a better example. So I have a superconductive temperature of Tc equal to 250. So how likely are these chemical compositions and atomic positions? Or maybe better, which chemical composition and atomic positions are likely to give rise to a Tc of 250K? So that would be a generative algorithm. You know what's the target, and you want to predict to get out the features. So in that case, you can also generate synthetic data, because you know to go from yi to xi. So I don't know, yi dogs, and then xi, I can get an image of a dog, right? So that is and a fake one, right? Because it's generated by the network. And the way it's done, it's through one of the ways. There are two ways. Variational autoencoder, we'll not talk about that, but we'll talk about generative adversarial networks. So the idea here is that you have a generative models, and you train two networks that compete against each other. So what you do, you have in order to then generate realistic data. So you have a generator, and the generator starts with they call it noise. It's simply a random vectors. And then there's some deep learning network here that from a random input will generate data, G of Z. That is fake data. Then you have real data from your data set, and then you put that to a discriminator, which is another neural network, and then this discriminator is in charge of saying, okay, this to discriminate, is that real data or fake data? And so that is, and this will give the prediction. The idea is that these two networks compete against each other because the generator wants to make fake data better, so it will fool the discriminator. So, and the discriminator wants to get better and figuring out what's the real data and what's the fake data. So that if the generator is forced to generate better fake data and so on. So that is why it's adversarial, because they have opposite objectives. So the generator wants to fool the discriminator, making very good fake data, and the discriminator wants to figure it out what's the real and what's the fake one. So it's a very nice idea. There's a formulation that we will not go into the details for the interest of time, but you can think about this as really zero-sum games, because they compete against each other, and the discriminator and the generator. So that's GANs in a nutshell. And it turns out that you can generate very realistic samples. That's why they became so popular. This is from NIPS 2020, so those last month. And these are images that these are not work of art. They are really generated by the GANs. That was trained on work of art. Maybe more interesting is these are tissues. So I don't know exactly which kind of tissues, but they are medical tissues. So you can generate fake data from there, and the thing is that you can train the network maybe on this fake data and get a better algorithm for predicting. I don't know here, I think it's for breast cancer, but I'm not sure. And so this is quite remarkable that GANs can generate very realistic samples in that through deep learning. And now we another machine learning application that I think is quite interesting, and I want to see if I will share my computer. Let's see if it works because I want to show you a small video. So what neural networks are also used for symbolic regression. So what is symbolic regression in a nutshell? So you have a regression that search for a mathematical expression, and you need to find a model that fits the data set that you have. And usually, as a starting point, you have mathematical building blocks, and you have heard this in other lectures in this class. And so that is symbolic regression. So essentially, you have an input, a data like as a table, and then you want to find the symbolic formula for that. And there is some very recent work where Tegmark group uses neural networks to predict a analytical formula starting from data directly. So now I want to see if I should be able to share my screen, because I wanted to show you this video. Let's try this. So I thought that since it would be pretty cool to have actually the author tell you about this paper, because I think it's pretty cool when they use neural network to predict, to come up with mathematical formulas for that. So then we have a 3-minute video when there's like the authors discussing this. So there you go.
And it's a pleasure to tell you about Pareto-optimal symbolic regression, exploiting graph modularity. Symbolic regression is finding a symbolic formula fitting a data table. For example, Kepler spent 4 years doing this until he discovered that Mars moved in an ellipse, revolutionizing astronomy. Symbolic regression is widely believed to be NP-hard for generic functions. Graph modularity refers to the fact that many functions that actually appear in science have a computational graph that's modular. For example, this function of 3 variables can be decomposed into 2 functions of 2 variables. Our method discovers this modularity automatically by training a neural network to fit the mystery function, and then checking if its gradients have certain special properties. We do this recursively until modules get simple enough to solve, and then combine the pieces to solve the original problem. So you can think of this as a recursive divide and conquer strategy of breaking the problem into simpler pieces. Our earlier work auto-discovered merely some special cases, but our new method has the potential to discover any graph modularity involving any functions of any number of variables.
I'm Silva Mariano Dresco. Pareto optimal refers to the fact that we evaluate not only the inaccuracy of each formula, but its complexity too. And we keep only the simplest formula for each accuracy level. Here, as you can see, we are able to auto-discover not only the relativistic energy formula, but also its classical approximation, mv²/2. We measure complexity in bits using an easy-to-compute compromise between Occam's razors and Solomonov algorithmic complexity. So how well does our algorithm work? We tested it on data tables from 4 different sets of equations. We chose 100 of the most famous equations from Feynman's lectures on physics, 20 harder equations from graduate physics textbooks, 12 equations with generalized modularity, and 10 probability distributions whose samples were converted to density estimates using normalizing flows. As you can see, we are able to solve the vast majority of the mysteries, achieving state-of-the-art performance. We also discovered that our MDL-inspired Pareto frontier approach is several orders of magnitude more robust to noise compared to our previous work. The 3-word summary of this talk is pip install AI Feynman, which is all you need to type to install our code on your computer. We'd love to collaborate on analyzing your datasets or on generalizing this approach to other domains.
All right, so you should hear me again. So that was about that. I think it's quite a cool application, and it's very new, so I thought I'd share that with you. And now we have a couple of more minutes, and I want to conclude the lecture. Let me share again my screen. And I want to tell you about what deep learning cannot do. So let me just go through this. This is about interpretability. We can go through that later, but I want to first go to the limitation, because I told you about how great deep learning is and what people have been doing and how exciting that is. But there are limitations, and one should be always aware of that. So in particular, I looked at this blog and I found it very, very good. So Cholet is the main developer of Keras and now a Google AI researcher. And what he says is that anything that requires reasoning is out of reach for deep learning model, no matter how much data you throw at them. And the reason is that, as we saw, the deep learning is just a chain of simple transformation. They are continuous symmetric transformation. We saw that, and so you're mapping from the input manifold to another manifold through a affine transformation and nonlinear transformation. So one will say, okay, it's what he says is that, well, it's not so surprising that deep learning cannot reason. I would say it's accomplishing lots of tasks, but also it's failing dramatically in some settings. So there's lots of work to do. Deep learning hasn't solved lots of problems yet, and you can see, for example, sometimes these are some examples. So you have the network here that you have an image, and then this is the prediction of the network. So the boy is holding a baseball bat, right? So really no understanding of the network. Or adversarial examples, when you have a panda here, and then you get some noise input vector, and then you are able to fool the network. And so what it says, and I think I agree quite a bit with that, is that one very real risk with contemporary AI is that misinterpreting that what deep learning models can do and overestimating them. It's a really big risk. So, why? One of the reasons you can think about is a high level, why deep learning models do not have an understanding of their input. Think about it. So what we give the network, we give input data and the classification for that, right? And that's all the network gets. So it is much different than you don't give anything of the process of us, right? Classifying that example, what comes in our mind, that's a dog or that's a cat, or why that we think that's an insulator or a metal. So that is something that you should always keep in mind. especially since you're a scientist, so you want really to think about this and not oversell deep learning. And one last thing that I want to mention is that we have a couple of minutes more. I really wanted to mention that part now. It turns out that one of the limitations of deep learning is also interpretability, because it's kind of you can see it as a black box model. A lot of people see it this way, and it's because it's hard to interpret. And deep learning models are hard to interpret because you have millions of parameters and the knowledge is distributed across that. Although that is difficult, there is work in interpreting neural networks. And here I post a resource from a PhD student actually at the Ludwig Maximilian University of Munich, and it's very nice blog post, and it's actually written like a book about interpreting neural networks. So I find it very, very good. And in particular, I will just give you one slide of what is the SHAP method, which is arguably, it's very, very used commonly to interpret deep learning model. And it unifies a couple of methods that are available in the literature. And the idea of SHAP is called the Shapley additive explanation, is that you use a game theoretic approach to explaining the output of any machine learning model. So that's what SHAP does. The idea is very simple. There's something called SHAP value, and you calculate the importance of the features by comparing what the model predicts with and without that feature. So you know how much that feature contributed to the model. So that's the idea of the SHAP values. And if you do let's say the going from game theory to machine learning, let's go to game theory, for example. You have a coalition of players that cooperates and they have a goal. Then some players contribute more or less to the coalition, so you don't know how much people contribute to. And the goal that the Shapley value has is it tells you how important each player is to the overall cooperation. And that you can calculate through the Shapley value. And if you think about the machine learning application, you have an overall gain that's in this game theory, where it gets substituted by the prediction and the player importance. So how important is the player with the overall game? That's substituted by the feature importance. So the contribution of SHAP is also that they provide a computationally feasible way to compute SHAP value, because they are combinatorial explosions. So that's what's the main work of Lundberg and co-worker. And to conclude here, there's an example actually using SHAP in material science, and they looked at predicting modeling the Latent constant using machine learning, and they use the SHAP value. So you can have a look at that, what would be an application of SHAP in material science. And I think we are over time. So I conclude this lecture. So I hope I share with you what deep learning is about, what deep learning can do. We went from NLP to CNN to recurrent neural networks, and then towards the end, generative models. And so then I will say that that's all. And again, thanks Luca, Matthias, Santiago, and Claudia for inviting me to give this lecture. In the remaining time, I'll be here and I will tackle the question that you have. Just also type them, or you can even spell them out loud. So thank you very much. Yes. So there is one question from Max. In Lstm, one should also apply nonlinear activation function in the memory state CT. Yes, so you do have you actually have fully connected layers in the Lstm. So I didn't go into the details. Let me just show the actual architecture. Yeah, so we are here. So what you are asking, Max, is how do you actually, update the memory cell? And so here you see that you learn from a given an hidden state. You have something called forget gate to say how to make the network decide through a fully connected layer with an activation function that is actually tan h, this like between 0 and 1 that you say, okay, do I keep the information from the past or do I forget it? So that is learn. And so that's the forget gate. And then the input gate also has, it has also a fully connected layer, and it tells you, well, do I put new input in the cell, in the memory cell? So so that is, you have lots of layers to really update the cell state, as you said. So yeah, you're definitely right. Yeah, so thanks a lot, Luca, for pointing out. So Luca is mentioning that one should mention that AI refinement of similar symbolic regression, deep NNN, deep neural network approaches implementations cannot currently select variables and features. And that is the right way to solve that is to comprehend sensing. And there is a tutorial by Luca and great work by Luca on that. And so this is what, thank you very much, Luca, for pointing that out. So I see there's a question by Max. So he's typing. You can also talk, Max, if you want.
Oh, okay. So it's better to talk then. No, just to summarize, my question is, we have seen a lot of developments in this deep learning applications for material science and chemistry with many different things. So my general question is, what do you think, in your opinion, that will be the trend for the next years in this field? It's more in this unsupervised learning side. I mean, the deep learning application for unsupervised learning or for supervised learning, something that is still missing and people is working more, and what we can expect for the next for this year and for the next few years in advancement. So.
Yeah. So it's of course I can just give you my opinion on that. So I see in general in deep learning people are trying to work on unsupervised learning for a long time. Because, as you know, label data is scarce, and so there is some degree of success with some sort of self-supervised learning or even using GANs to get new input data. So I think unsupervised learning can be a good trend, but it's hard, and maybe there's not even good enough models for that yet. I also think that I'm pretty excited. I would be pretty excited about generative models, especially in your field of application, because at the end, I mean, at least the way I see it is that often you are interested in coming up with a material with a specific property, and so that is the other way than saying I have a material. What is the property of this material? So kind of going back, I think it's quite it will be quite an exciting part, and so generative models, and I think it's a very good way forward. I know there's some there was some earlier work in molecules on with variational autoencoders like a couple of years back, so it might be something, I think, something interesting to look at in that regard. So the development you saw also regarding this Polynet and Ferminet looks also that people are working more, some work trying to do optimization, solving optimization problems. So that is also maybe something that will come later, using the flexibility of deep learning frameworks for that. Yes. Another thing that another trend in general in deep learning that because I attended the conference, it's called New RIPS, and there's it's an important conference in deep learning, and there was a lot of work on bias. So people were saying, okay, you know, there's a bias in the data, then the models at the moment don't do anything about that. So they were saying, okay, that's something. There's a community of deep learning. People can look at that. And that could also be something interesting for material science, because you have some sort of, I mean, as we all know, the material science space is practically infinite, and you probably have a small sample of that. And so it could be also interesting to see what are the new directions there where people try to tackle biased data, and then maybe you can also think about applying that to some sort of bias because you have a limited subsamples of the possible materials.
Thank you very much for the answer.
Yeah.
Sometimes when we just are starting in the field, it seems that everything is solved because there are a lot of papers appearing all the time.
Mm-hmm.
So it's good to have in mind what could be eventually some directions to invest more time. And, yeah, thank you.
Cool. There's no further questions. So then thanks again for the invitation, and thank you for the questions and interactivity, and looking forward next time. Bye-bye.
Bye-bye. Thanks a lot.